Hello and welcome to this video. In this video we're going to look at Rutherford scattering. So we're making a start on nuclear physics. We're going to start talking about the nucleus of an atom. How do we know the nucleus exists? What was our evidence for that? We're going to look at radiation that comes from the nucleus. We're then going to look at things like fission and fusion and everything that comes along with all of this nuclear physics stuff. So let's first start this video by recapping a little bit of the timeline of the nucleus, or of the atom in general. So first of all, way back in ancient Greece, they assumed that things were made up of things they called atoms, which basically is just atoms, and they believed that that was the smallest thing that could possibly be. Okay, but then we found that we could actually have parts of the atom that were charged and parts of them that, but overall an atom was not charged. And that's what led us to the first real model of the nucleus, or of the atom in general, which is the plum pudding model. Now the plum pudding model is you just have an area of positive charge with some negative charges embedded in it. So you have an area of positive charge with negative charges embedded. Okay, so you've got negative charges that are just embedded in this positive area so that you have an overall neutral charge. Now, we obviously know today this is not the case. This is not how we think about atoms. And the way that we realize that this is not true is because of Ernest Rutherford and his experiment of Rutherford scattering. And what we're going to go through in this video is kind of looking at Rutherford scattering. What did it mean? How did it occur? So let's first make a start on what the setup of this experiment was. So this was just an experiment to try and demonstrate a theory of the atom. Now, most of you will probably have heard of Rutherford scattering from GCSE or something along those lines. And those of you will be able to remember that he started off with just an alpha source. So he had some sort of radioactive material that was constantly emitting alpha particles. And he basically fired these alpha particles with some velocity at a thin sheet of gold foil. So this is just a thin sheet of gold foil. And obviously these are alpha particles. They're not just going to travel indefinitely. They're going to lose energy pretty quickly. They don't really have a very large range. So we had to put this inside a vacuum chamber. So he put it inside of this vacuum chamber. And the reason he had this vacuum chamber, if I write that over here, so he had a vacuum chamber. And the whole point of this vacuum chamber is to prevent collisions. Prevent the collisions with the gas particles, so that the alpha particles don't collide with gas particles, decrease their energy and decrease their range. If we fire alpha particles with like zero energy or very, very little energy at this thin sheet of gold foil, none of them are going to pass through because it won't have the energy to pass through, right? It needs a certain amount of energy to actually be able to pass through some sort of object. So we need to try and make sure that the energy remains above that kind of threshold. And the last part of this setup was he had a detector. Now this was like a Geiger counter or something like that. We'll look more at these kind of detectors and how they work in a different video. But he had this detector, and this was a movable detector, so he could rotate it basically anywhere he wanted around this kind of vacuum sealed bulb, and he basically just performed this experiment. He fired these alpha particles at this thin sheet of gold foil, and he just measured where he could see these alpha particles. Now, his observations, I will try and write down here. So his observations, the first thing that he noticed was that most of these alpha particles were just traveling straight through the middle. Okay, so most alpha travel straight through. Okay, most of them weren't stopped or deflected or anything like that, so he detected most of them right at the opposite side of the gold foil. He then started to rotate the detector around, and he found that he could actually detect some of them through some small angles, which means they've had some small deflection. So some alpha were deflected through some small angle. So I'm going to say small angle. And the third thing that he noticed, and probably the most significant thing that he observed, was that if he came all the way around to the other side, he can actually detect a very, very small amount of them that are being reflected off of this sheet. So his final and probably most important observation was that about 1 in 10,000 alpha particles were deflected back, or we could write it as through 180 degrees. They were deflected all the way back. Now, alpha particles themselves wouldn't have the energy to be able to collide with a whole atom and then bounce back and move this far to get to the detector. It would have stopped in midair before it ever reached it, which means that it couldn't have been a collision with this thing. It had to have been some sort of repulsion. This was the first idea of his conclusions from these. So now we have the observations. Let's now look at the conclusions that we can pull from each of these. So the first one is fairly straightforward. If most of the alpha particles travel completely through this thin sheet of gold foil, it must be mostly empty space. If we want to, alpha particles are not exactly small particles, right? There's still 2 protons and 2 neutrons bound together. It's a helium nucleus. It's not tiny. So for it to be able to fit between 2 atoms, it must mean that the atom itself was mostly empty space. Okay, so atoms are mostly empty space was his first conclusion. Mostly empty space. Now, his second observation, that some of the alpha particles were deflected through some small angles, kind of hints towards there being some charge there, but it's not a definite conclusion that there is a positive charge there. It's when you combine the second 2 observations that you can actually definitely conclude there has to be some sort of concentrated positive charge. So there must be a concentrated area of positive charge. How do we get this conclusion? Well, if we were to think of the size of a helium nucleus, the only possible way that it could be deflected back or even deflected through some small angle is that it has to have some sort of electrostatic repulsion. This is our hint towards it being positively charged. Okay, in order for it to have a 1 in 10,000 chance, what we're saying is that we have a nucleus that's like this big, and we have an alpha particle that's about this big, or actually if I were to scale it up a little bit, let's have a nucleus that's about this big, and our alpha particle is only about this big. If this is then going to have an alpha particle here traveling past, this is going to deflect through some small angle. Okay, now if some of them were deflected through some small angle, it means that they've got the space to pass by, but if only a very, very small amount of them were deflected straight back and came straight back to where they started, deflected through 180 degrees, this must mean that we have a much smaller area of positive charge than we do the empty space. So we have to have a concentrated area of positive charge, and this is now what we know as the nucleus. Now, obviously, we also know that the nucleus has neutral charges in. At the time, they weren't familiar with neutrons yet. So they concluded that it must be a positive charge in the center. And then Niels Bohr went on to then describe how the electrons move in their shells. We don't really have to know too much about that because this is nuclear physics. We're more focused on the nucleus and what happens inside the nucleus than the electrons. For those of you who are doing chemistry, you will know that we then go on to get the nuclear model, which talks about orbitals and all of that kind of stuff. And actually the orbitals and all of that just comes from quantum mechanics that you can do for anyone who's going to university. You can derive all the shapes of all the orbitals from just very basic Schrodinger's equation. I'm getting off topic. So what we've got from this video is that we have a experiment set up in order to narrow down this idea that from looking at the observations of these experiments, we can therefore draw these conclusions. We know that most of the alpha particles were traveled through means that we have atoms that are mostly empty space. We have some of them being deflected and a very, very, very small amount of them being completely deflected backwards, means that we must have a small area of positive charge, which we know as the nucleus, and the Rutherford scattering is our evidence for the nucleus of an atom. Now it does also tell us one small other thing. Using some probabilities, we can say that actually the diameter of the nucleus is therefore 10,000 times smaller than the diameter of the diameter of the atom. So if I had this is the full atom, right, and let's say it has some diameter which I'm going to call big D, and it has some nucleus, and that has a small d for the diameter, then what I'm basically saying here is that if I did d over small d, this would give me 10,000. Okay, so by probability, based on this observation at the top here, that 1 in 10,000 alpha particles were deflected, we can make a rough assumption that the nucleus of an atom is roughly 10,000 times smaller than the atom itself, which then proves that we have a much, much smaller concentrated area of the positive charge. So the nucleus is actually a very, very small amount of an atom in terms of volume. So this is Rutherford scattering. This is how we know the nucleus exists. Thank you for watching.